Hello and welcome to this NUKE 226 Painting and Reconstruction Techniques with NUKEX. My name is Victor Perez, and in this first class we are going to talk about tracking. Because in NUKE we have three different kinds of tracking. The first one, the easiest, is the 2D tracker. Then we have the 2.5D, which is the planar tracker, and then the 3D tracker, which is the camera tracker. Let's start analyzing when are we going to need one of them, because we are not going to spend a lot of time using a 3D tracker just for something that can be done using a normal 2D tracker. So when are we going to use the 2D tracker? Well, the 2D tracker is something that allows us to create the same kind of transformations as you can find in the transform. So you can create translation, rotation, and scale. That is not much because as soon as we get perspective, we cannot perform any kind of tracking in there. In the tracker, in here, we can get a corner pin by positioning tracker feature in every corner of, for instance, this billboard, and then matching that, creating the corner pin. But the corner pin is going to mimic what is the perspective in 2D. That is why we call it a 2.5D. But to be honest with you, the 2D tracker or the tracker node is not that good to generate the corner pin by that technique because it's really easy to get a lot of artifacts. The planar tracker is going to create not only 4 points to calculate that, it's going to create a lot of points, exactly that amount we can select in here, this number of features, inside a shape. For instance, in this case, in this shot that we get perspective on this wall, we can place a shape and track this plate in here. Let me put it in here, something like that. We don't need to be precise at all in here because everything is at the same plane. So when I track this surface, everything is going to be tracked inside this shape using this amount of features. So if I press the preview features, as you can see, is going to locate the best features to calculate not the single movement of those points or the average, as the 2D tracker is doing when we are selecting more than 1 point, which is averaging the movement. In the planar tracker, the maths in here are just calculating the relation between all those points that are 100 points to create and mimic the perspective shift of this shape. So by using that, I can match not only the translation, rotation, and scale, but also the perspective as we get in here. Here you are. Of course, we can use the planar tracker just to use the translation or the translation and scale and the scale and rotation, or translation, scale and rotation, and everything with the shear and perspective. Perspective is the most complex movement we can get. Now remains the third option, which is the camera tracker, the 3D tracker. And this one is slightly more complex than the other. So in here, we are going to recreate the volume of this scene. As you can see, the camera is moving freely inside this street. So if we want to track something in here, something like the wall or the pavement or whatever we want, is maybe better just to get everything at once. For that, we get the triangulation of those points based on the calculations of the camera tracker. So let me explain better this technology. What we are going to analyze using the camera tracker is a 2D image. So based on triangulation of the positions, we are going to understand the volume of this scene. But in order to create the triangulation, we need to calculate where every point is going to be on each frame. So it's going to be a space-temporal triangulation. So we are going to triangulate the same point. So this is the 2D view. Of course, this is the camera, the lenses, and this is the scene. So we are going to put features, which is the same as a normal 2D tracker. And in this 2D tracking phase, we are going to track the movement of every part of this geometry. So using those features, we are going to understand how the geometry is going to move in the real 3D space to recreate a virtual 3D space. But the principle behind all of this is the principle of parallax. What is the parallax? Well, the parallax is what you experience when you look through the window and you are traveling on a train. So things that are closer to the train are moving faster than things that are far from the train. And this principle makes your brain understand that something is big and far and something is smaller and closer to the train, even if your perception is slightly the same. So you don't see the perfect 3 dimensions of the volumes in the distance, but by the movement you can create the volume. So imagine that this is the first frame. Let's call T1. And then we're going to create the movement to another time and a space, of course. So let's imagine that in the second time, so in frame 2, for instance, this piece of wall is going to be maybe here, and the cube, which is the small one, is going to be maybe here. Okay? So by using that, we can get now other positions. So let's put that on yellow. So this, and now that, and this. Okay? So based on the difference between those points, I can understand that there is a certain amount of parallax. So we can create this feeling of movement now by using the principles of triangulation, so the theorem of Pythagoras. To explain that, we need to understand what's happening inside the lenses. So let's create a line from this top area of the cube, going through this side, and now from this one, here on the bottom, that are going in the opposite direction. Here you are. So this is now revealing an effect, which is the image from the outside inside the sensor is going to get upside down. So the image is going to look something like that. Okay? So this is absolutely normal because the image is going to be flipped from this special point in the lenses. This point is called the focal point, where all rays of lights are converging inside the lenses. And this point now is creating two triangles. We are getting the first triangle in here, which is the triangle we need to calculate, the outside triangle, and then we have the inside triangle. Well, for the outside triangle, we don't have a lot of information because this is the real 3D space, and the only thing we get when we are analyzing the image is this thing. But if we know a few data, we can get a lot of information regarding the triangulation. Because how can we know the distance of these rays of light from this point in the camera? Well, in maths, if you get two triangles with the same angles, like in here, and you know all the sides of one of them, You can project the same triangle by creating the correspondence of at least one of the sides. So those triangles are going to be proportional. So first of all, we need to understand the size of these lines. And is that possible? Well, let's try to get it. First of all, can we know this distance in this triangle? Yeah, of course we can, because we know the sensor size. So every camera has a sensor, or in the case of a film camera, we have a film bag. And we know the size of that because it's specified in the characteristic of the camera. So we can know the width of the sensor and the height. So if we know this distance, we can easily get what is the distance between this point and this other point. So here we are. We have now this side of the triangle. Let's call this A. Okay? So now we need to understand what is the size of this side and this other side. Well, we don't know much to get this, but if we know the distance between the focal point and the sensor, maybe we can create some kind of arrangement to calculate that. And of course we know that because the distance between the focal point and the sensor is known as the focal length. And every lens has a specific focal length. So yeah, we know this distance as well. What can we do with this distance? Well, if we follow this axis, we can project a line from this focal point directly into the sensor. So now this has created two triangles. Now we know this side of the triangle that we are going to call B, and now we only need to know this side. And if we know A and we know B, applying the theorem of Pythagoras, we can know this side of the triangle. And voila, we got this side. Using the same process, we can get this other side. So now, here we are. We know the angles and the sides of this triangle. Now, it's just project this triangle to the outside. Of course, the only thing we need is to create a relation between this distance. As soon as we get the relation between this distance, we can apply the same proportion to all the sides of this outside triangle. And we can calculate that by surveying on set and specifying that from this point to this other point, in here, we can get a certain amount of distance. So we can create the proportions inside NUKE specifying those features. Of course, if we are working strictly with projections, we don't need any special proportion. The proportions are needed when you are working with physics or when you are exchanging data from one software to another to be aligned with the same size. But for us, for this course, mainly we don't need the proportions of this triangle. So here we are. Now we know how to get the triangulation done for every single point in the scene. And by using the space-temporal offset, we can understand the parallax between the front side of this cube and the front side of this other cube. This is the theory for the triangulation of the points, but in order to get the volumes, we need to assume that everything in the scene is still, is not moving. And the perception of the movement we are getting in the plate is because the camera is moving. So this is why we call it camera tracking, because we are tracking the movement of the camera. But in order to get the 3D movement of the camera, we need to get the parallax between the elements. So in order to get the parallax, we need the camera to move to reveal that parallax and that volume from the scene. This is the theory behind the camera tracker. But in order for this to work, we need to calculate the triangulation not inside one single frame, but from one frame to another based on the same point. So with that, we can get the differences in the volume, so the parallax. And we are assuming that everything in the scene is steady, and the only thing moving is the camera. Of course, we are going to get elements in the scene that are moving, like people, for instance. We need to rotate them out. We are missing something important in these calculations. And that missing point is the lenses. In 3D world, I mean the virtual 3D world, we don't get any lenses in the camera because, of course, the camera in the 3D is just a point of view to render the pixels of the 2D view. But in real world, cameras has lenses, and that lenses has a distortion. Why? Because in here, in the lens, we get this portion, which is a section of a sphere, something like that. What is actually happening is rays are not straight when they are getting out of the camera. I mean, when they are coming from outside to the inside. The projection of this triangle in the distortion of the lenses should be something like this. Which means the farther away you are from the center, the axis of the lenses, the more distortion you are going to get. And this is actually a real problem for the calculations of the triangle, because we said that we can project this small triangle inside the lenses outside, but we know that if we project this with the problem of the lens distortion, this is not a triangle anymore. So what can we do for this? Well, we can remove the lens distortion. And this is a very delicate part of the camera tracking, because getting a good lens distortion pattern is going to solve way better our triangle in here. If we get something like a margin of error, our triangle is going to get far from the original point, and this is going to create an error of solving. So we need to calculate, first of all, the distortion of the lens. So let's have a look at the ways we have in NUKE to calculate that and how to apply to the camera tracker.
So let's go ahead and call the lens distortion node. In this node, we have three methods to calculate the distortion: the image analysis, the grid analysis, and the line analysis. The first one I'm going to use is the more precise, which is the grid analysis. For the grid analysis, we need a lens grid. And what is a lens grid? Well, a lens grid is something similar to this. It's an array of lines, in this case based on the checkerboard, so the lines delimited by the squares. And the lens distortion node is going to analyze the squares and calculate the distortions of those lines and apply that distortion to the whole plate. So let's analyze this checkerboard. The best thing of this method is precision and speed, because it's super fast to calculate and is quite precise. If you want to check if this distortion has been correctly removed, you can use this align grid. But remember, this align grid is just for testing purposes, not for calculating the distortion. So this is going to make the lines, horizontals and verticals, to get aligned with the edges of the plate. So it's going to be really easy to analyze the lines in the checkerboard. The second method we are going to calculate is the image analysis. The image analysis is going to base the calculations on features across the whole plate. So based on the motion of those features when they are getting closer to the edge, is going to calculate the distortion of the lines. So in order to get that, of course, we need to mask out everything that is moving in the plate. So for instance, in this plate, the cars. So I'm going to prepare a roto to get this thing out. So here you are, the mask finish. So I have masked out the cars. So now we can select in the lens distortion the analysis range. So I don't want to track the first frame, so I want to start from frame 2 to 201. The camera is a free camera because the movement is free, it's not a rotation. And for the mask, I'm going to use the source alpha, as in here. So it's not going to calculate the space in the cars, because the movement of the cars can create errors in the calculation. So let's analyze this and let's see the result. Now the only remaining option is the line analysis. So let's go ahead and call another lens distortion node. For this method, what you need to do is to locate straight lines in the plate, just trace a drawing line to help NUKE to calculate, based on those lines, what is the exactly amount of distortion on those lines. So let's go ahead with this line, for instance. So I'm going to enable the drawing mode. You should be as much precise as you can be. The problem is sometimes the lines probably are looking like straight, but they are not so. So here you are. Okay, when you finish drawing a line, you press the right click, and now we have the first line. Try to be as close to the edge as possible and try to draw a few lines. The more you put, the better is going to be the calculations, but try to be as accurate as possible. So I'm going to put another line in here. Let's be precise on the pixel, and in here, and in here. Right click, and I'm going to put a few more lines. So I have now my lines, and the only thing remaining is to analyze them. So let's analyze, and now it's giving me this result that is, again, slightly different from the other two calculations. So this one is the line analysis. Good. So we have the three methods. Each one is different from the other, but in my opinion, the grid analysis is, of course, the most precise one because it's based on more mathematical calculations and less human error or computational error like the image analysis, like in here, or the line analysis. The line analysis is going to be the less precise because it's going to depend a lot on the precision of your lines, and your lines, of course, need to be as precise as the pixel and the resolution of the picture. So those three are the methods we are going to use to remove the distortion. You can use the method you prefer, but the important thing is you have to remove the lens distortion before to start doing the camera tracking. So once you get your lens distortion removed, now you have in here this undistort. So the lens distortion can be used for both remove the lens distortion or put the lens distortion back. Why should we need to put the lens distortion back? Well, in the virtual 3D world, we don't have lens distortion, but in the real world, we have it. So what we need to match is the virtual 3D world to the real world. So we are going to work everything inside the virtual 3D space without the consideration of the lens distortion. But as soon as we render any patch or painting or even geometry, we need to apply the lens distortion back in order to match the same ratio of distortion from the original plate. So now that the lens distortion is not a problem anymore, let's go ahead and track the camera for this plate. And the camera tracker is going to ask me for a few details regarding my shot. And it's going to ask me what kind of camera motion is. Well, we have rotation only, free, linear, or planar. Well, those three are going to assume a certain kind of movement of the camera. Based on the movement, is going to create a certain kind of calculations. But the first one, the rotation only, is going to create a lot of issues, because with a rotation only, we don't get any kind of parallax. And if we don't get parallax, we cannot get the volumes. So with the rotation only, we are going to get kind of a 2D movement of the camera. So it's going to be like a non-volumetric solve of the scene in 3D. So there is no way of seeing any depth in the 3D space. It's going to be helpful just for the movement, but it's not going to be very helpful with the creation of geometry. So this is a free camera. Now, the lens distortion. As we removed the lens distortion before, we can say in here that we don't have any lens distortion, so we put no lens distortion in here. So now that we have removed the lens distortion, the only thing remaining is the data for the triangulation I mentioned before. So the data we are missing now is the focal length and the film back, which is the same as the sensor size, that we can use from one of the presets we have in here. But what's the camera and what's the lenses we are using for this shot? Well, if you go to frame 0, you will find this slate containing this data. So it's telling me that the camera model is Sony X1 and the film back is 6.97 by 3.92 millimeters. So let's put the focal length at known, and I can tell you that the focal length we use for this shot is 5.8, and the camera model is in here, which is the Sony X1. So now we have everything we need to know for start the tracking process. So let's have a go with the tracking and let's see the result. So here you are the result of the 3D tracking. As you can see, we get the perception of the volume and the 3D space. So in here, this is going to be really helpful to reconstruct part of the buildings or the floor or any other feature that is not moving inside this scene. So now that we have an overview of the 3 different types of tracking we have in NUKEX, we can now create a checklist to understand when it's going to be better to choose one or the other. So the first one, the obvious option, is going to be the 2D tracker. This is the fastest way to get a tracking done, but you can only use that when you get only translation, rotation, and or scale. Okay? And if you are using rotation and scale, you need at least 2 points. Okay? So if you are including the perspective, you need to apply at least the 2.5D, so the planar tracker. So for the planar tracker, you can get translation, rotation, scale, and perspective. But you don't get a 3D scene of it. It's just a 2D representation of a virtual 3D space, but it's a 2D operation. This is good because it's going to be faster than the 3D. Still, you have limitations. Sometimes, even for the planar tracker, you need to get lens distortion. The last one, the 3D tracker, is for everything else. So when you are getting a 3D space involved, something like a reconstruction of different planes, you are going to use the 3D tracker because it's way better to having a perception of the volumes and the 3D space. But of course, sometimes can get tricky if you get a lot of things moving in front of the camera. For the lens distortion, something that we need to keep in mind is you can export the lens distortion for being used by other people even when they don't have the NUKEX version. So with the non-X version of NUKE, you can apply the lens distortion by using this process. So I'm going to use this lens distortion pattern, and if I go to the output type, instead of seeing the image, I'm going to place a displacement. So in the displacement, it's going to place in here, in the forward, it's going to place this UV. So this UV is actually mapping the distortion. So if I export this as an OpenEXR, I can get this forward. And let's export that as in here. Let's go to the desktop. And now here in the desktop, let's call it lens distortion underscore v1 EXR. I want to save it as EXR because I need full precision in here. So I'm going to place 32-bit float to get every tiny variation of this green and red channel, okay? So once I have that, let's hit render. I just need one frame, so let's put it in here. And now I'm going to read that file. So here you are. And now to apply the distortion, of course now is in the forward, I need to use the STMap in here. So STMap. And now, where is my source? This is the image I want to distort, and this is my STMap. And I have to indicate where is the lens distortion pattern. So I need to go to other layers, forward. And now what is going to happen is I'm going to move on the RGB. And now, as you can see, it's applying this pattern of lens distortion. So with this, just sharing this OpenEXR image, you can use the STMap and you don't need to apply the lens distortion node that is available only for the NUKEX version. So now we got the lens distortion workflow and all the tracking features ready to be used for you for start painting out people in Mexico. But this is something for the next class. Thank you very much for following this course. I look forward to seeing you in the next class. Until next time, this has been Victor Perez for FX PhD.